Welcome back, AP Statistics, for the 26th and final chapter of the book, Inferences for Regression. We're going to be returning to the topic of regression, and we are going to be combining that old knowledge with our newer knowledge of inference involving hypothesis tests and confidence intervals. So let's look back at our old friend, the scatter plot. To the right is a scatter plot showing a positive linear relationship between waist size and percent body fat in a sample of 250 men. So you have waist size on the x-axis and percent body fat on the y-axis. In Chapter 7, remember Chapter 7, that was a long time ago, we fit least squares regression lines to such data. The least squares model for this set of data is the predicted, and that's what that hat means on top of percent body fat, the predicted percent body fat, the predicted y value, is equal to negative 42.7 plus 1.7 times the waist size. And you will recall that variables are, we would say, meaningful. It's not just x and y, it's waist size that helps us estimate the percent body fat. So now we're going to talk about something called the idealized regression line. The regression line that's perfect, the idealized regression line. In Chapter 7, we used a model of the form y hat equals b sub 0 plus b sub 1 times x to describe a linear relationship between two variables. In theory, there is an ideal regression line that is true regression line for the entire population, right? So that regression line in Chapter 7 with b sub 0 and b sub 1, that's for sample data. Now we're going to talk about a regression line for the entire population. We would say this ideal regression line, the regression line that models the entire population, not just a sample, is of this form. Mu sub y is equal to beta, that Greek letter is beta, beta naught plus beta 1 x. Note that b sub 0 and b sub 1 are estimates. They're point estimates for beta sub 0 and beta sub 1. So you may have been wondering, okay, I get that the betas are going to be estimated by the b's, b sub 0 and b sub 1. But what's the deal with mu sub y? All right, so here's a little description as to how we get that. We know that for each waist size, there is variation in the percent body fat. All right, so waist size does not perfectly give us a percent body fat. There's some variation, right? Just like with everything in statistics. Here, for example, is the histogram of men with size 38 waist. We see there are all different percent body fat counts for these men with a size 38 waist. We could imagine the true least squares regression line to be the line created by the means of the distribution of percent body fat for each waist size. To visualize that, we would have a picture like this. In such a case, each point on the least squares regression line would be of this form. You have an x value, and then for the y, you have the mean of the y values for a particular value of x. And those would form the ideal least squares regression line, the least squares regression line for the entire population. So now we need to talk about the concept of error. When we talked about least squares regression lines a while ago, we had to talk about this concept of error. Least squares regression lines, they don't fit data perfectly, and that's kind of the point. They're supposed to show a trend. That means that relative to the regression line, which it gives us predictions, actual data values are going to differ a bit from where the line says they should be. And that difference we call error. So, of course, most, if not all of the data are not located on the mean of the distribution for each waist size, so they wouldn't fall on the regression line. Hence, relative to the population regression line, each data point in the population has a small error, which we will call epsilon. If you recall, error for a sample was called E. So error for the population regression line is called Greek version of lowercase e, which is this little backwards 3 fella that we call epsilon. It's a Greek lowercase e. Errors are random and can be positive or negative. Okay, they can be positive or negative. So thus, for each data point relative to the ideal regression line, we can say that y value for the point is right along this regression line, except it's a bit off. Okay, so here's the regression line itself, but this y value is not on the regression line. It's going to be off by a little bit. It's going to be off by epsilon, which means that it's going to be a bit above the regression line if epsilon is positive, or a little below the regression line if epsilon is negative. So similar to how we would approximate the betas with the lowercase b's, we approximate epsilon with the residuals of our sample data, which we call E. So for sample data, a residual is the observed y value minus the y value that we'd find by plugging x into the regression line. Now, there are some assumptions and conditions that we need to perform inference about the coefficients, that is beta sub 0 and beta sub 1 for the ideal regression line. So if we want to find confidence intervals and test hypotheses about beta sub 0, that would be the y-intercept, as it were, of the ideal regression line, or beta sub 1, that is the slope of the ideal regression line, we need to check off some boxes. And I'll just tell you right now, there aren't really any applications for doing inference on the y-intercept of the ideal regression line, beta sub 0. It's all about beta sub 1 in this chapter. That's really all that matters. Are there applications for inference on beta sub 0? Yeah, but not in this course. We need to assume linearity. The scatter plot follows a linear pattern. The book calls this the straight enough line condition, or just the straight enough condition. The scatter plot looks generally like a straight line that is not curved. The independence assumption, this is an oldie but a goodie. The errors must be independent of each other, all right? We can't have some errors affecting others, some data values affecting others, producing errors that are influenced one to another, all right? And we can check that using the randomization condition. Data need to be collected from a random sample or a randomized experiment, and the random residuals condition, all right? And we're going to be talking a lot about residuals. This is the first thing I'm going to say. The residuals plot created by our scatter plot and least squares regression line for our data has no pattern. So we look at the residuals over here, and you'll note right now that this is 0, a residual of 0, which would mean that the data point is right on the regression line. And the further the points are from 0, this horizontal line that would mark a residual of 0. The further they are, the more they are off the beaten path of the regression line. This set of residuals is wonderfully boring. We want boring residuals. These residuals are not boring, all right? They form kind of an arch, all right? And that is our arch enemy right there. We do not want residuals to form any recognizable pattern. That would mean that a linear model is not appropriate for our data, and analysis of the data is going to depend on whether we can transform it to be linear using the methods from Chapter 9, a personal favorite of mine, or it might be beyond the scope of the course. Our next criterion we call the equal variance assumption. That means that the variability, however you measure it, variance or standard deviation of y, should be the same for all values of x, or essentially the same. Looking at this plot right here, we see a good example of essentially equal variance for all values of x. It doesn't matter what value of x you pick, we end up seeing y values, some of which are a little high, some of which are a little low, but they vary about the same no matter what value of x you pick. We could kind of put guardrails on either side, and they would pretty well model the traffic, as it were, of the points in the scatter plot relative to the middle of the road, as it were, that is the regression line. So that's what equal variance looks like in bivariate data. So the spread of points relative to the regression line needs to remain constant. And how do we check that happens for sure? Well, we have this humorously named "does the plot thicken" condition. All right, do not say "does the plot thicken" on an AP test. I'm sure there are some students out there who are going to say it, and it is probably humorous for AP graders, but please do not say it that way. Here's what you need to check. We need to analyze a residuals plot like this one here that actually has predicted y values on the x-axis. That's one way of doing it. A residuals plot like this, where as the predicted y values, you could also do this with the x input values. You can choose between the two. As these increase, the residuals start pretty small, but then they get wildly unpredictable. And you have this fan pattern. Now, if you thought we were all done with the conditions, unfortunately, I have some bad news. There are not one but two more that we need to consider, and they involve a different representation of the residuals, as you see the histogram on the right side of this slide. We need to assume a normal population. So not only must the distribution of the residuals for the ideal regression line be consistent, as we talked about on the last slide, but it must be nearly normally distributed, like we see in our histogram to the right. That is unimodal and symmetric. So we check with the nearly normal condition. The distribution of residuals is unimodal and symmetric. This is a great example on the right-hand side. If we were to plot the residuals in our stat plot, if they stack up like this, we are good. Also, the outliers condition, there are no outliers among the residuals. Now, mind you, if there is one outlier or two outliers, but the vast majority of the data appear to be roughly unimodal and symmetric, or unimodal and symmetric enough that we could put a good enough trophy next to it. If you remember a couple chapters ago, then we're just going to continue with the study and acknowledge that perhaps we need to take our results with a grain of salt because there were a couple of outliers that demand some explaining. So here we go, the ideal regression line under ideal circumstances. If the ideal regression model is linear, the data points show signs of independence, which we detailed, and the errors vary equally and are nearly normally distributed with no outliers, we can assume our ideal regression line model looks like the figure to the left. All right? So for each of these x values, there's a bit of variation. But if we consider the means of all that variation, those means would form a line. And that line is the ideal regression line. Thank you to the textbook for this very helpful image and description. So now we're going to actually get to a practice problem. That was a lot of introduction. Here we go. Look at the moon with binoculars or a telescope, and you'll see craters formed by thousands of impacts. The Earth, being larger, has been hit even more often. Meteor Crater in Arizona was the first recognized impact crater and was identified as such only in the 1920s. With the help of satellite images, more and more craters have been identified. Now more than 180 are known. These, of course, are only a small sample of all the impacts the Earth has experienced. Only 29% of Earth's surface is land, and many craters have been covered or eroded away. Astronomers have recognized that a roughly 35 million year cycle in the frequency of cratering, although the cause of this cycle is not fully understood. Here's a scatter plot of the known impact craters from the most recent 39 million years. We've taken logs of both ages in millions of years ago and diameter, that is in kilometers, to make the relationship a bit simpler. All right, so we did some data transformations like the ones in chapter 9, and these data are looking pretty linear. So can we perform inference on these data? Well, we have to check off some of the checkboxes, or really all of the checkboxes if possible, to make sure that we can perform inference. All right, so we start with the linearity assumption. The scatter plot satisfies the straight enough condition. All right, the scatter plot, this one right here, where we did some data transformations, does appear to fit a straight line, or rather a straight line would be a good fit to analyze these bivariate data. Independence assumption, the size of impact craters are likely to be generally independent. All right, there you go. It is an assumption after all. But how do we confirm that assumption? Randomization. These are the only known craters. All right, so it's not really random. We're just taking the known craters that we have. And they may differ from others that may have disappeared or have not yet been found. We need to be careful not to generalize the conclusions we get too broadly. There may be a reason that we found the ones that we found and not found the ones that we haven't found that may have something to do with their size. That's a pretty reasonable assumption, okay? So we got to take our results with a grain of salt. But the further you've gotten through this book, the more you realize that we got to do that a lot in statistics. We just need to be careful about how much we generalize. Random residuals condition. Now we look at the residuals plot here. The residuals appear to be randomly scattered, no recognizable patterns. Does the plot thicken? After fitting a linear model, we find the residuals shown. All right, so we have these residuals over here, and we have residuals over here. The plot does not appear to thicken. Yeah, there's a little bit of thickening down here, but it doesn't appear to thicken all that much. And the nearly normal condition, okay? A histogram suggests a bit of skewness in the distribution of the results. It does appear to be a bit left skew. However, at very least, it does appear to be unimodal. I mean, if you were being a real stickler, you could say maybe there's something bimodal over here. Nah, it's probably unimodal. A histogram suggests a bit of skewness in the distribution of the residuals. There are no violations severe enough to stop my regression analysis, say the writers of the textbook, but I'll be cautious about my conclusions, all right? We want to be bold, but we also want to be humble, all right? Now, there are, as you saw at the bottom, 2 points that seem to give the impression the residuals may be more variable for higher predicted values than for lower ones, all right? But this doesn't seem to be serious violation of the equal variance assumption, all right? So if we look at these residuals here, there is a bit of mess down here that breaks up our equal variance assumption. But that is, like I said before, it's 1 or 2 values that are a little out of the ordinary compared to the vast majority that are behaving quite well. Whatever.